All right, so last time we studied IPv4, subnetting, fixed length subnetting, mask, and variable length subnet mask, and we have already provided the videos for the packet tracer as well. So I hope you guys are following those and you're having some practice, because these are not easy topics. They need a lot of hands-on practice. So if you're just following lectures, I must repeat that you must also watch the videos for the labs and attempt those labs yourselves as well. Otherwise, watching these videos or just attending these lectures won't help you. You might understand things right now, but when it comes to hands-on practice, you need reinforcement of these learnings again, and hands-on skills on the devices and configuration as well. If you're not doing that, remember that you will very easily forget that. I have been in this field for more than 10 years, and I also forget these things, and I have to revise them every time I come across these topics. Every time I have to open up books, notes, or search on internet, I have to revise these things again and again and again. So it's not one-time learning. You have to learn it again and again, and that's how you do the reinforcement of the learning, so you keep what you learn. Okay, so please follow those things, follow these instructions, and keep practicing. We're moving on to the IPv6 now. In my opinion, IPv6 is easier than IPv4 because we don't do a lot of subnetting. We don't do VLSM, fixed length subnetting. It's really straightforward. Reason being, IPv6 is an improvement over IPv4. So obviously IPv4 was complicated due to the subnetting, network address translation, and all those things, saving the IPs because we're running out of IPs. All those problems has been solved in IPv6, and that's why IPv6 is easier to understand, in my opinion. In a lot of, it would look a bit difficult in the beginning because it's new thing. You're more familiar with IPv4, but once you really follow through with IPv6 and you get the basics, it is easier than how IPv4 works. It's much simpler, and that's what we are gonna focus on today. Okay. So IPv6 addressing. So in this module, we're going to talk about what issues we had in IPv4 and why IPv6 was needed, and how IPv6 is addressing these issues and solving these issues, and how do we, and what are the different categories of IPv6 addressing. Just like we had in IPv4, we had public IPs, private IPs, then classes, then subnetting. We had PIPA addressing, we had local host addressing. So there are, all those sort of things are still available in IPv6, but it has some extra stuff as well. Okay. Right. Of course, we have packet tracers as well, and as usual, we will be providing you packet tracer labs for the videos as well. Okay, so what were the IPv4 issues? As we discussed these before, let me get my pen. So IPv4 is 32-bit address, and 2 power 32 is roughly 4 billion addresses, and around the world 4 billion addresses are not enough because we have more than 4 billion devices connected even right now, but it's still working because in IPv4, to conserve IP addresses depletion, to conserve the IP addresses, we kept introducing new ways to save the IP addresses, like private IP addresses, so that everyone in their local area network can use the same IP addresses repeatedly around the world. So that's how we save some IP addresses. Then to make it work with public IPs, we introduced a network address translation so that the private IPs could be translated into public IPs, so that those IPs and their traffic could be routed across the internet. And that's how we're connected at a home with private IP addresses. Our routers is doing network address translation, and that's how we get internet. But even still, with all those technologies and solutions to save and conserve IPs, these are the regional bodies that assign public IP addresses to the internet service providers in this region. So we have ARIN, BRIBE, AFRINIC, APNIC in Asia, and LACNIC in South America, North America. We have ARIN. These are the regional registries and bodies that are responsible for giving blocks of IP addresses to the public IP to the internet service providers, and then eventually each internet service provider gives a public IP to each connection at home, right? And they know that they're running out of IP addresses. So whatever was allocated to them, and they kept announcing that in 2015 we will run out of our IP4 addresses. RIPE announced that we will run out of it in 2012, Afternic in 2020, AppNic 2014, and so on. Of course, we're still in 2025 and we're still using IPv4 addresses and we haven't run out of it. The reason for that is that we keep introducing new technologies and new methods to reuse the old IPs. There are organizations that are buying public IPs from each other. So initially there was a lot of waste in public IPs because small organizations bought a lot of public IPs which they really did not need it. So single organization took like one block of /8, a class A address in the beginning. One organization will never need a /8 block of public IP addresses, but they bought it and they own it. Nobody can do anything about it. So right now there are a lot of organizations, they can buy public IPs from each other and transfer it to each other, and that's how they're getting around. These are workarounds. So we still need to move to IPv6. It's 2025. We're still using IPv4, but we must move to IPv6. And recently, a lot of organization has already moved to IPv6, but remember, we cannot just move to IPv6. IPv4 is a reality. We cannot just one day say that, hey, we're no longer working with IPv4. From today, we are going to work with IPv6. No, IPv6 has to roll out dynamically, slow, gradually, one by one. And there are solutions on how to do that, and we're going to discuss that next as well. But the reality is that IPv4 needs to go and IPv6 needs to replace it, okay? Why? Because IPv6 has 128-bit addresses, and 2 power 120-bit is such a huge number that we will never run out of those IPv6 addresses, okay? It's not just a big number. IPv6 also included fixes for IPv4 limitations and other enhancements as well, which we are going to talk today about. That what are other things that are different in IPv6 other than just being a big number, big 128-bit addresses. Okay, so with an increasing internet population and limited IPv4 addresses, we introduces network address translation to preserve IPv4 addresses. But remember, NAT is not a desirable protocol. I mean, we wish if we could, we don't want to use NAT. Why? Because NAT introduces delays and it breaks end-to-end connectivity because IP addresses change when we use NAT, and some application like video and voice application would rather not have a NAT to work better and give you a better performance. But NAT is a reality. It's still there with IPv4. And since we also have IoT devices coming in, our air conditions, refrigerators, home appliances, all of those Internet of Things are also connecting to internet. So we need more and more IP addresses, right? So all these things combined are forcing everyone to transition to IPv6. It's not just a big number that we are running out of IP addresses. There are more to it. We want enhancements. We want optimization. We want speed, okay? We want simplicity. And that's why we're transitioning to IPv6. So now to transition to IPv6, it's not a one day, one click, or with a snap of a hand, we can move to IPv6. We need solutions to transition to IPv6. So IETF, the body who is responsible to create solutions and to transition everyone to IPv6 around the world, has proposed or created these solutions, a dual stack solution, a tunneling solution, and a translation solution. So the first thing is dual stack. That is something you are going to see in a lot of devices on your personal computers, on your laptops, on your mobile phones, on the routers, and everywhere. You're going to see a dual stack solution. What is a dual stack solution? A very simple solution that every device from now on, all the modern devices must support both IPv4 and IPv6 protocol stacks simultaneously. So in parallel, all our computers, all the routers, all the mobile phones come with both stacks. They have IPv4 installed, they have IPv6 installed, and you can run both of them at the same time, depending on whichever the device wants to use or whichever is available. Okay, so IPv6 would be preferred by every device if it is available and everyone is connecting using IPv6. But since we understand that not everyone can support IPv6 or not everyone has implemented IPv6, that's why we also have an IPv4. So if they don't, if there's something that cannot talk with IPv6, we will by default use IPv4 in those cases. So that's how we're forcing everyone to transition to IPv6 by having them both. And slowly and gradually, we want to eliminate IPv4 and fully transition to IPv6. But this is going to take a long time. It's not like 1 year, 2 year plan. It's like maybe it's been planned since 2010 or even before that, like since 2000s. There have been research and people talking about that we're running about IPv4. We need to transition to IPv6. And still organizations are struggling to transition to IPv6. Maybe it would take 10 more years, maybe 20 more years, nobody knows. But IPv6 is already here and it's running simultaneously on all devices right in parallel with IPv4, and we're going to see that on our machines today. Okay, another method is called tunneling, a method of transporting an IPv6 packet over an IPv4 network. So the IPv6 packet is encapsulated inside an IPv4 packet. So if you have a situation where you have a PC that only has IPv6 addresses and it's connected to a router, and then their router is connected over to the internet to other devices, and there's another PC that's also running IPv6, maybe these are two branches of the same organization, but they have taken this connectivity, WAN connectivity from another ISP, right, to connect together. So maybe it's a city to city wide area network connection, it's the internet connection, whatever. So probably the ISP still hasn't transitioned to IPv6, so it is running IPv4. So, but your organization decided to use IPv6 on both ends. But the internet connection that you took is IPv4. The ISP doesn't support IPv6 yet. They haven't transitioned. They're still working with IPv4. So in that case, you can use tunneling, which is a method of transporting an IPv6 packet over an IPv4 network. So you have an IPv4 network. Of course, this device must have IPv6 enabled, at least these end devices. So even if the middle, everything is IPv4, all the connection within ISP, these IPv6 devices can create a tunnel over this IPv4 network. What is a tunnel? Tunnel is just an encapsulation method that you have a packet that is generated by this computer, and it has source and destination, and it uses IPv6 addresses, right? If it sends it to this device must also support IPv6, obviously, but every device in between is not supporting IPv6. So what this device can do is it can incorporate something called tunneling. So what is a tunneling? It can encapsulate this entire packet back again in IPv4 packet. So it can use the IPv4 addresses here again, and it hides this whole IPv6 packet. So all the devices only see IPv4, and when it reaches its destination devices up to which the tunnel is created, it would remove the IPv4 header and expose the IPv6 header and forward that IPv6 header to this device. So these devices still communicate using IPv6 together, but the packet is basically tunneled through the IPv4 network in order to reach that IPv6 header. So that's another solution if your internet service providers or the middle devices are not able to support IPv6 yet, but you still want to transition to IPv6, you can use the tunneling method to make it work for now. There's also a translation method which says network address translation 64, which works just like NAT, but for NAT 6 to 4. 6.4 means 6 to 4. So network address translation. So a device sends an IPv6 source and IPv6 source and destination addresses, just like this situation. But instead of creating a tunnel, the end device, the router or your wireless access router, what it can do, it can just remove IPv6 address and instead use its own IPv4 address in the source and destinations. And keep a table entry with itself, like a network address translation table, in which it keeps an entry that, hey, this IPv6 address is basically this IPv4 address, which is translated to it. And then it uses IPv4 to route the packet, and the final destination gets the packet, and you get a reply back. When your reply is reaching back to this device, it translates it back from IPv4 to IPv6, and you get an IPv6 packet in a reply again. So there is a device that can do translation, just like your wireless access point is doing translation from private to public. Similarly, devices can do IPv6 to IPv4 and IPv4 to IPv6 translation. These are just methods created to help speed up the transition to IPv6, okay? The tunneling and translation methods, these are something you would not see usually. What you would usually see is that people using dual stack. So the tunneling and translation are really special type of technologies that you would only see in special cases, okay? Right. So these are the methods that we would be using. You might see it as well. So how do we represent IPv6 address? We have seen IPv4 addresses. Let's look at the IPv6 addresses. So IPv6 address is 128 bit in a length. It's written in hexadecimals. We have covered those before when we were covering binary decimal and hexadecimal counting systems. IPv6 addresses are not case sensitive. So if it has a or a small a, that's again same thing. So because in hexadecimals we have A to F represented for representing 10 to 15 digits, right? But these F could be a small, it could be a capital letter. It's not case sensitive. It still means the same thing, okay? The preferred format for writing an IPv6 address is to have 1, 2, 3, 4, 5, 6, 7, 8 hexadecimal. This one hexadecimal is represented by 4 hexadecimal digits, which means 16 bits. So you have 8 of them, right? So you get 128 bits. So each one is called hexadecimal. In IPv4, we have octets, which represents 8 bits. And here we have hexadecimal, which represents 16 bits or 4 hexadecimal digits. A hexadecimal is an unofficial term used to refer to a segment of 16 bits or 4 hexadecimal values, okay? So usually IPv6 addresses look like this. You have 8 hexadecimal, and in each hexadecimal you are represented using 4 hexadecimal values. So you see a 2 or a 0 or a D or a 1. This is not a decimal value, this is a hexadecimal value. Each hexadecimal is basically representing 4 bits. So in a hexadecimal, you have 4 hexadecimal digits. So each one is representing 4. So these 4 hexes are actually representing 16 bits, okay? So this is how normally IPv6 addresses would look like. And there are shortcuts to shorten these IPv6 so we can type and read them quickly. And we're going to discuss those things. How do we do that? Okay. So there are some rules to have a shortcuts in writing or reading an IPv6. So the first rule is to reduce the notation of IP addresses to omit any leading zeros. So if we have this address, you can see if inside any hexadecimal you have leading zeros like this one, or multiple leading zeros like this one, you can simply omit them, like don't even write them. It's not needed. So this address, we can remove all the leading zeros inside all the hexadecimal. These are all leading zeros, so you don't have to write it. So in short, you can write the same address like this, okay? I don't think there's any, I don't think there should be any confusion in this. It should be very simple and straightforward that you should be able to read this again, and you can figure out if you have 1 0, that's actually meaning there are 4 zeros. We're just omitting first 3 zeros. And if you just have DB8, you can figure out that, or a computer can figure out that, hey, there couldn't be 3 hexadecimal digits. There has to be 4 hexadecimals. So that means there's a leading 0 that's just hidden. We don't write it. Similarly, for all 0, if you see single 0, that just means there are 4 zeros. We just omit the leading zeros. Similarly, for 200, it just means this is 0200. Actually, the 200 is a shortcut. So there has to be four digits in a hex state. That's how you can figure out, or a computer can figure out, the exact full IPv6 address, even if you do shortcuts. Okay, that's one rule. We can do further shortening if we have continuous zeros of hex states. For example, these zeros. So you have a zero. One hex state is a full zeros, full of zeros. Another hex state is full of zero. Another hex state. No matter how many hex states you have in a zeros, you can replace them simply with double colons. Because it's zeros, we don't really need to type it. We can shorten it further. So this address, which is the same address that we previously saw, we were just omitting zeros, but when we omitted zeros, it became like this, right? So there's 3 zeros, continuously 3 zeros hectates. What we can do with it is that instead of typing all these 3 hextates of 0, we can just type double colon. But remember, you can only do this once. So this 0, we cannot replace it with double colon, so 2 colons or double colon. How do you pronounce it? How do you want to pronounce it? Double colon is fine. Okay, so you can only do this once within an address. So for example, if this address was 2001 0 0 1 1 1 1 and then 0 0 0, I'll just type 0, right? 0 0 0 0 200. If you had zeros, continuous zeros here and 2 continuous zeros here as well, you cannot do it like this. Like you think I can do this, convert this into double colons, and then you have 1 1 1, and then you have continuous zeros, convert this to double colons, and then 200. This is wrong, because you can change the continuous zeros into double colon or replace it with double colon only once in a single address. So you would do it for the longest number of zeros, whichever you want to pick. You can pick it anyone. You can do it for either for this or this, but usually you would want to do it for the longer number of zeros. And over here, you would have to type it exactly as it is. Okay, so you cannot do it twice. You are only allowed to do it once. Reason being, because if you do it once, then the computer can look at this address and figure out how many hex states there are missing. So you have 1 hex state, 2 hex state, 3, 4, 5, and then you have a double colon. So the computer can figure out that we are missing 3 hex state, so it can insert back 3 hex state, all with zeros. So it can figure out the exact address again by looking at this address, right? But if you do it twice, then the computer has no way to learn how many hex states are missing in which location. So let's say you create this address. If you do it twice, right? You have double colon here and double colon here. So now you have 1 hex state, 2 hex state, and 3 hex state. The computer knows that it's missing how many hex state? It's missing 5 hex state, right? It's missing 5 hex state, but how many and where? It can add 3 hex states here and 2 here, or 2 here and 3 here. So it doesn't know. It cannot be sure. That's why you cannot do it twice. Okay, so that's another rule. So this is how we write short addresses. All right. There are different types of addresses, just like in IPv4. In IPv4, we had unicast addresses. So similarly, we also have unicast addresses in IPv6. Unicast uniquely identifies an interface on IPv6 enabled device, just like in IPv4 address. The unicast address is one address. If you send to that destination, that is an address of a single host device. That packet is forwarded just to one host alone. That's why it's called unicast. That IP address belongs to just one interface of a host. Okay. A multicast address, similarly, again, we had multicast in IPv4 as well. What's a multicast? Multicast is used to send a single IPv6 packet to multiple destinations. So that's an IPv6 address, a special IPv6 address. If you send a packet to this special IPv6 address, the routers or switches, it will forward it to multiple devices who belong to this group. So that's a special address, multicast, which would be forwarded to all those devices who have joined that multicast group. Okay, so one IP address belonging to many devices. So that's not one-to-one. That's not a unicast. That's why it's called a multicast. If you send something to that destination IPv6 address, it will reach to multiple devices because multiple devices are part of this single IPv6 group. That's what we call multicast. We don't have broadcast in IPv6. Remember what was a broadcast in IPv4? If you send a message to an IPv4 broadcast, so broadcasts are two types in IPv4. It's 255, 255.255.255.0, and also in each subnet that you create, the last address is like 192.164.0.255 in /24. The last address of every subnet is also broadcast. So one is a local broadcast, another is called directed broadcast. So the broadcast addresses are, if you send a message on a broadcast IPv4 address, all the devices inside the local area network would receive that broadcast. Broadcast means it's for everyone, okay? No device can say, I don't want to receive it. Everyone has to receive it inside the network. So we have removed broadcasts in IPv6. Why? Because broadcast causes problems. Broadcast eats up a lot of bandwidth. It eats up a lot of resources like RAM and processing power from intermediary devices and all other devices, okay? Because you can send one packet and that packet send to thousands of devices if you have thousands of devices in your network. So broadcasts are not efficient, right? So we don't want to use broadcast. Although if you want to achieve the similar kind of result like the broadcast, you can use, we don't have broadcast address, but there is an IPv6 all nodes multicast address. We're going to see what is IPv6 all node multicast address. That essentially gives the same result. So we can get that result from the special multicast address if we want, but we don't have a special broadcast address, just like IPv4 in any subnet, okay? So in IPv6, if you have a subnet, all the IPs are usable IPs. You don't have like, hey, this is a broadcast IP and you cannot use it. That's not the case. We have a special type of IPv6 addresses that are called Anycast, and which is in IPv6 unicast like an address that can be assigned to multiple devices. So you have a single IP, but you can assign it to multiple devices, usually just 2 devices. So you assign the same IP to 2 devices, and it's considered an Anycast address. And if you send a packet to that destination, that Anycast IP, which acts like a unicast, you would think you're just sending an IP to a single device. But in reality, there are 2 devices that are configured to have the exact same IP addresses. So what happens in that case? A packet is sent to an Anycast address is routed to the nearest device having that address. So any device that is near to the source will receive the packet. So it has you have an advantage with that. It's a new type of Anycast. So if you have a PC that wants to send a message to a special IPv6, it looks like a unicast, but it's in Anycast. So you have a network, and then there's a PC here. So let's say it's a Google server, right? And then there are other Google servers. So you don't have one Google server. So there could be other Google server connected in a different region. That's also a Google server. So they both have same IPv6 address. So your computer wants to access Google. You get an IPv6 address from the DNS. You want to send a packet to this address. It's a simple IPv6 unicast type of address, but both of these computers have it. Who will receive it? The routers will route it to the one that is closer to you. So if there was another user that was connected here, and if it wants to send to the same IP, his packet would be received here because this is the nearest one to him. So that's the benefit of using Anycast, that whoever is closer to whichever destination, although both have the exact same IP, but your packet would be only routed to the one that is near to you. So that has its benefits. So that's a new kind of or new type of IP address that we don't have in IPv4. And you can already see that in IPv6, we have made improvements over IPv4, and there are things that are not possible in IPv4 or were wasteful in IPv4. We have removed it from IPv6, and we have added new capabilities into IPv6 as well. Okay. So prefix length is something that we have studied in IPv4 as well. What is the prefix length? The prefix length is actually what is showing you what is the network portion and what is the host portion. So similarly, like in IPv4, we also have prefix lengths in IPv6 as well. And it can range from 0 to 128. Okay, you can have a /0 as well. You can have /128 as well. But normally that is not the case. Normally, almost always, as far you are concerned as a beginner in this field, you would see a network of /64, which is right in the middle, right? So you have 64 networks and a 64 host bits, if you talk in terminologies of the IPv4. But right here, we don't talk in those terminologies. IPv6 has its own terminologies. So the first 64-bit, if you're working with /64 prefix, the first 64 bits are now called prefix, or in other words, a network portion. And the last 64-bit would mean the interface ID, or in other words, in IPv4 terminologies, this is the host portion. Right here, we would call an interface ID, okay? So an example is like this. As you can see, so this is the IPv6 address, 2001, this is the first hexes, DB8, colon A, and then you have 2:/64. It's a shortcut. It just means 2001 DB8A, and after A, how many hexes we are missing? We are missing 5 hexes. But now we're saying if you're missing 5 hexes, that means all the hexes are just zeros. So the full address is 2001 DB8A 0000. All hexes are 0. Okay? And /64 just means the first 64. If you expand this whole address, you would get 2001 DB8 0 0. This would be the prefix, because 1, 2, 3, 4 hexed, because it's right in the middle. /64 means right in the middle. The left portion would prefix, and then the right portion would be your interface ID or a host portion. So this would be your interface ID. This would be your prefix. Okay, so this is how this IPv6 address actually looks, and the /64 means this is your network portion or prefix, and this is your interface ID, and this is how it's written here. Okay, so now what is an interface ID? Interface IDs for most network are using 64-bit. Obviously, this is what you are left with, 64-bit IDs for the networks, and there is a method that is called stateless address auto configuration, or in short, it's called SLAAC, which uses these 64 bits for the interface ID. It also makes subnetting easier to create and manage. And we're going to discuss like what is SLAAC, and if this is all zeros, what does it mean for the device who is eventually getting an IP, the interface? What is the actual interface ID? It is just zeros. We're just defining that this is the network. That means all these bits can be used to create unique interface IDs, just like we have in IPv4. If I say 192.168.0.0/24, that means this is the network portion, the 0, this is the host portion, meaning the host portion, we can keep incrementing the host portion, right? And these are all the usable IPs up to 254, because 255 is just a broadcast, right? That's not usable. So similarly, when we say this is the interface ID, that means you can keep incrementing this one. Of course, this is in binary, but if you want to type it in hex, so this becomes 0, 0, 0, 1. So this is in a hex, then 2, then 3, up to F, and then the next one would be 0, 0, 1, 0, and 1, 1, up to 1F, and 2, 0, so on. These are all the actual IPv6 addresses that you can assign to routers or hosts, right? But in reality, when it comes to IPv6, we don't choose or increment IPs, and we don't even manually assign a lot at all. We use this SLAAC method, which will create this interface ID uniquely for each interface or each device automatically. So we don't have to type or manually do this. And we are going to look at that process. How can all the computers or interfaces on the routers can automatically assign themselves unique IP addresses just by getting this prefix? If they just know what is their prefix and what is these 64 bits are their interface IDs, and they pick an IP inside this interface ID, they create their own IP addresses. That's what the SLAAC means. We're going to look at that in a while, okay? Right. So the IPv6, so types of IPv6 unicast addresses. So the unicast addresses are where we're focusing, right? Which is where we are interested, just like we are interested in IPv4 addresses. Like there are different types of IPv4 addresses. What are the different types? Like you have public IPs, you have private IPs, you have local host IPs, you have APIPA. The APIPA IP is when you don't get an IP from DHCP, so the Windows device can get themselves IP 169.254, right? That's the APIPA IP. And then there are multicast and different. Similarly, we have an IPv6 as well. We have different types of unicast addresses. We have global unicast addresses, which is like public IPs. Okay, so in IPv4 we call it public IP. In IPv6 we just call it global unicast. These are the IPv6 addresses that can appear on the internet. The routers will route it, and these are the only IPs inside the IPv6 that can be routed on the internet, just like the public IPs on the IPv4. All other types of IP addresses in IPv6, they can be only run in specific cases, but they will never appear on the internet, okay? This also means the global unicast addresses are the one that internet service providers will provide to you. You cannot just assign it to yourself. So these are the public IPs that, again, IANA would do the exact same thing like it's doing with IPv4. It has public IPs or global unicast IPs. It divides them in different regions for different continents, and it would give each continent its own block, and those regional bodies would then assign other blocks to different internet service providers, and then the internet service providers give you a home connection through which it only gives you a single public IP. So those are the global unicast. Those are called global unicast in IPv6. Okay. So this is similar to public IPv4, and they are globally unique internet routable address. That's what this sentence means. Okay. Then you have link local addresses. These are special kind of addresses that we don't have an example for it in IPv4. Okay. They work a little differently. They are required for every IPv6 enabled device and used to communicate with other devices on the same local link. Link local addresses are not routable and are confined to a single link. These are special addresses that any device that is capable of doing IPv6, that has an IPv6 stack installed, must have a linked local address. So in that sense, it is just like a private IP. It is inside local area network. It cannot be routed on internet, but it is different than IPv4 address, IPv4 private IP addresses in a sense that they are required. Every IPv6 device that is using IPv6 must have linked local addresses, no matter what. Even if they have global unicast address, they still need a link local address to function. So no IPv6 device can function if they don't have a link local address, okay? But link local addresses are only used inside a link, in a single link. So if you have two routers that are using IPv6 here, it is also using IPv6, it would have a link local address here, LLA. And this would also have a link local address. They both can communicate with each other using this link local address. But this IP is not reachable from, let's say, here. and if this is computer is also v6, or even if it was a router, it cannot communicate to the other router over the hop. Because why? Because these required for every IP65 and used to communicate with other devices on the same local link. That's the thing, same local link. So this is the same local link between these two routers. They can communicate using these addresses together, but another router cannot communicate it using this IP. It would need a global unicast address to communicate with it. Okay, so it's like a local area network, but it is must needed. Okay, then again, it also has a loopback, just like we had in IPv4. 127.0.0.1 or the entire 127 block /8. That was a loopback in IPv4. In IPv6, you just have :1/128, and :1 means just all zeros in the beginning. So you have 7 hex steps of 0, and the last one is just 1. That's your link local or loopback. That's your local host IP or a loopback IP, which you can ping, which means the packet would be sent to yourself to get, it's looped back to yourself. It's not going anywhere. It's just for testing your own stack, that if it's working or not. Then we can test it on our computers right now, which I'll do in a while. I'll show you these things on my computer. Unspecified address. This is wrong. I don't know why it is there, but let's ignore this for now. Unique local addresses. So these are the addresses that are like private addresses, like private IP addresses you had in IPv4. Okay, they start from FC00::/7 to FDFF. If you see an IPv6 address that is starting from either FC or FD, that means that is a unique local, which is like a private IP addresses like 192.168 or 10.0 or 172.64, right? Which means it is limited to inside local area network, but it is different than link local addresses, because the link local addresses are must. Every device must have it, no matter what. Unique local address, you can choose if you want to, but these IPs, just like private IPs, are not routable. You won't see them on the internet. Why would you do it? Maybe some devices or some organization want to use these IPs if they never want to connect to the internet. And there are organizations that never want to connect to the internet. Then they can use unique local addresses inside their location, which would make sure that they can never connect to the internet. There are highly secure data centers. They're called air-gapped networks. Okay, so this is a terminology that is also, this is not CCNA related terminology. You won't see it in CCNA level, but you won't see it at a CCNA level, but you will see it in your job descriptions maybe, or in some networks with customer when you are working on real projects, that somebody says, hey, our network is air-gapped. What it means is that we have a network that is not connected to the internet. You cannot work on that network remotely. You cannot connect to any devices remotely. You must go to that site physically and work on the devices. That's what air-gapped network means. They cannot connect to internet for security reasons. So that's where you would use the private IPs or unique local IPs in IPv6 to make sure that they can never get to internet. Okay, so unique local are different than link local address. And then we have embedded IPv4 for working with IPv4. So IPv6 addresses can also look at IPv4 address on a device and create an IP address for itself that is created from the IPv4 address. Is a special kind in special situation that can happen. But the more important ones for you are to understand what is global unicast, what is link local, and what is unique local. And even more important in them is just these two. Link local must have. Every device must have, if it's using IPv6, it must have link local. If it wants to go to the internet, then it must have global unicast. These are the common ones that you should remember. Okay. Again, there is a slide on the unique local addresses, which is like private IP. So I've already addressed this, like what is a unique local. So unique local addresses are used for local addressing within a site or between a limited number of sites. Unique local addresses can be used for devices that will never need access to another network or internet, in other words. Unique local addresses are not globally routed or translated to global IPv6 address. Even if you want to route them using the global IPv6 to other means, that's not allowed. You're completely off the internet for other networks, okay? Who would use it or why they would use it? Well, many sites use this private nature of RFC 1918. RFC 1918 specifies the private IP addresses like 192.168 and 10.0s to secure or hide their network from potential security risks. This was never intended use of unique local addresses, but people want to use it that way. Okay. All right, so let's go back to the global unique addresses, which are like public IP addresses. So IPv6 global unique addresses are globally unique and routable on the IPv6 internet, obviously, just like IPv4 public IPs. And currently, only global unique addresses with the first 3 bits in binary, if it starts with 001, or if you convert it to hexadecimal, it becomes like this: 2000:3 are being assigned. So globally, IANA has only allowed this specific block of IPv6 address, which starts in hex from 2000. Okay, so the first hex is 2000/3. So the first 3 bits, you can move those only. They are being assigned to the entire world, to different continental regions, so they can assign it to their different ISPs. That's the only one that's being used out of so many that we can. Why? I don't know why. Mostly because we don't need those. This is enough for the entire world. If you just start with the 2000 :3. Okay, so it starts from 2000 and ends with 3FFF. These are the only global unique addresses that you can have at this moment in IPv6 addresses. So all the addresses that are on the internet on IPv6, they start from 2000 and ends with 3FFF. And if you see these numbers, you must know that it is an IPv6 address, a global unique address, okay? And which is the only, and this is only 1/8 of the total available IPv6 address spaces, which is enough for us. Okay, how does the structure look like? So this is divided in 3 different sections. You have global routing prefix, you have subnet ID, and you have interface ID. And let's see what these different sections in the global unique addresses mean. So the global routing prefix is the prefix or network portion of the address that is assigned by the provider, such as an ISP, to a customer or a site. The global routing prefix will vary depending on ISP policy. So just like you had a network section in IPv4, so we say /24, so we knew this was our network portion. The global routing prefix is that network portion, okay? So when an ISP gives you a public IP, it gives you with a prefix /24 in IPv4 cases, so you know that, hey, this is my network portion 192.168.0, the first 3 octets. That means this is fixed portion. I cannot change this. This is what my ISP assigned to me. I only can change the host ports, and then inside this host portion, you can do your subnetting, create multiple subnets, just borrow more subnets if you need more subnets, or just use this one subnet if that's the case. In IPv6, when ISP assigns you an IPv6 address, it will give you a prefix, and that prefix would define this global routing prefix, that this portion is your network. You cannot change this. This is what ISP gave you. After that, you have options to do your things, your own subnetting if you need it, okay? And that's where the subnet ID comes in. So in IPv4 cases, we had to create subnets ourselves. in this case, that is predefined for us as well. And you can change it as well, but usually we don't have to because now we have so many IP addresses. You don't have to worry about wastages. So the subnet ID field is the area between the global routing prefix and the interface ID. So it's the middle section. The subnet ID is used by organization to identify subnets within the site. So your ISP provided you an IPv6. It has a network portion that is called global routing prefix. You cannot change that portion. That is global routing prefix. Okay. Then you have a subnet ID. That's where you can keep changing. So if you have 00, that's one side, 01 is another side, 02 is another side, 03 is another side, or another subnet. You can call it another subnet. Just like we were doing subnetting within the IP that was given, within the network that was given to us. So we did fixed length subnet masks, right? That was the subnetting topic that we discussed. So instead of doing it ourselves, now we already have a subnet ID and we can just keep changing those IP to create more subnets. And after that, we have the interface ID, which will be the actual host IP within that subnet, so range of IPs that you can assign to the hosts. So the IPv6 interface ID is equivalent to the host portion on the IPv4 address. This is like a host portion. It is strongly recommended that in most cases /64 subnet should be used. As I said, you would most commonly see /64, so you don't have to worry about a lot of different subnets and do a lot of calculations, which creates a 64-bit interface ID. So we will see how this interface ID is created by each computer automatically. You don't even have to worry about assigning them unique IPs. Computers can do that themselves, okay? All right. So this is the structure of global unique addresses when ISP provides it. It's like a public IP. It has three sections. The global routing prefix that is fixed. You cannot change it. And then after that, you have a subnet ID and an interface ID, which you can change. The subnet ID will be changed for different subnets. So each subnet would have its unique subnet ID. And the interface ID would be the actual host ID or the IPv6 address of the interface that we'll be assigning to devices. That's the global unique addresses. Like if I remind you, we have many types, but we're focusing only on the global unique address, the global unicast address and the link local, okay? So this was the global unicast address. And this is the structure that we discussed and defined. And now we are coming back to the link local addresses. These are the addresses that every device must have no matter what. If it says it's an IPv6 device, it must have a link local address. It cannot exist without it. It cannot function without it, okay? So you can have an IPv6 device that does not have a global unicast address. That is fine. All devices don't need global unique addresses. Just like right now in IPv4, you don't need, all devices don't need to have public IP addresses. Same cases with IPv6. But they must have link local addresses to function. So in IPv4 addresses, if your device has a public IP, that's it. You don't have to give it a private IP. It can function and everything can work with that public IP on that device. It can do everything. All the networking facilities are available if you have a public IP. That is not the case with IPv6. Even though if you have a global unique address that is given to you by ISP and it's internet traversable and everything, you still need a second IP, which is link local address, because we said that an IPv6 device cannot function without it, even when you have the global unicast addresses, okay? So remember that link local addresses are very important. It enables the device to communicate with other IPv6-enabled devices on the same link and only on that link or subnet. So link local addresses are must, but they can only communicate with other IPv6 devices using link local address if they are on the exact same link or on the same subnet, okay? And we're gonna see what that means. So packets with a source or destination link local address cannot be routed. So if you want to send an IP address to link local address, it cannot be routed. So if there is a router and there's a IPv6 device here, and there's an IPv6 device here, and this one has a link local address, and this has a link local address, and if you want to send a packet to the router to forward it to this link local address, that's not possible. Router will not forward a link local address to another device. Okay, they cannot be routed. Every IPv6 enabled network interface must have LLA. Every interface must have LLA. If these are all IPv6 addresses, they all must have LLA, or link local addresses. Give me a second, guys. Wait a minute, I'll be back in a minute. Okay, guys, I'm back. All right, so every IPv6 enabled must have LLA, so we have that. If link local address is not configured manually on an interface, the device will automatically create one. It has to, because it cannot work without it. IPv6 link local addresses are in the FE80/10 range. So every time you see an address, an IPv6 address that starts with FE80, that's an indication that this is a link local address, okay? So we already talked about that. All the IPv6 devices that have link local addresses, they can communicate together, but if they are on the exact same link, like this one. So these two can talk to each other using link local address, but these two cannot talk to each other using IPv6 link local addresses, okay? Why? Because the router will not route link local addresses. In that case, they would need global unique addresses. So this gives you an example that link local addresses only work inside their own network. So if you had another link local addresses here, and you connect a switch here, and then you connect multiple computers here, and all these computers have link local addresses, they all can communicate together up to this point. They can all communicate to each other, all these computers and router, using link local address, but they cannot communicate to this router or this computer or any other network. They are just limited to talking to each other. That's it. And these are just limited to talking to each other. These are just limited to talking to each other. That's the purpose of link local address. Okay. I see people raising their hands. I believe there would be a lot of questions. So I'll just, usually I take questions at the end, but let's take questions right now. Okay. Who has a question? You can unmute yourself and start asking.
Yes. I have a question. Yeah, I think you just answered my question, because I wanted to ask that what if we have computers connected to a switch, and the switch is connected to a router, and all the...
Yeah, I lost you there, but I got you. So you got your answer, right? So if there's a switch and everything is connected together using a switch, and all the devices have link local IPv6 addresses, they can all communicate together. The communication stops when they reach a router, because a router will not forward link local addresses at all anywhere. So they cannot go out of their own network. They can only communicate within their own network using link local addresses. Okay. Anyone else has a question?
Yeah, I have a question.
Yeah, one minute.
Okay, go ahead.
Yeah, what's the best practice for link local addresses?
What is the best practice?
Yeah, what I mean is that is this advisable to configure link local addresses manually, or since the interface generates this address
The
automatically, there
yeah,
was the
so
need for manual
so the best
configuration?
yes, the best practice is the IPv6 says don't do anything manually. That's the best practice. Let the computers
Oh,
do
okay.
its thing. They can do it. They can figure out things themselves. That's why IPv6 is so superior over IPv4. You don't have to think about these things. It is doing everything automatically for you. It is just giving you an option that you can also get a manual link local address to a device. The only reason for that, and the only reason why you would do that, is just to have an IPv6 address that is easily remembered for you or easily identified by you, because when you assign it manually, you can give it something like FE80 : 123, another device 124, 125, and you easily remember which device has which local address. Instead of computers doing them themselves, they would just generate something that looks random and it wouldn't be easy for you to remember. If that is the case, if you just want to remember it and give it like a nice structure, you can do it manually. But if you don't do it manually, every IPv6 device will do it automatically. It will assign itself automatically a unique IPv6 link local address, and you don't have to do anything and it will work. So that's, I mean, that's the best practice. Don't do anything. You don't have to remember or make sense of it. It just works.
Thank you. Thank you.
Okay, next question.
I have a question. If you have, for example, 4 local area networks in 4 cities, and they are connected over routers and have dedicated fiber links, 100 kilometers, something like this. And we want to, they're working on IPv6, but because of security reason, we don't want to use any global part of addressing, and to go only through our fiber and like a air gap, but it's not real air gap. So how we are using IPv6 at this moment, and to our routers don't have any global addressing part, so we are not going global at all. How we are doing this?
So, I mean, if you have your own branches and your own fiber, right, and you have multiple branches and you have your own fiber, you're not taking any connection from the ISP, right? So you laid your own dark fibers. This router is also owned by you. There are routers inside branches that are owned by you. So then you're already not connected to anything else. This entire network is administrated and owned by you. It's not connecting to externally anything or internet. In that case, if these are all IPv6 devices, just like we talked about it, when you enable IPv6, or if it's by default enabled on these devices, all of these computers, hosts, these routers, they will create their own link local addresses automatically without you doing anything. And they have to do it because we talked about it. If there's an IPv6 device, it must have link local address, period. There cannot be a device that says I am an IPv6 device and IPv6 is installed and enabled on me, but I don't have a link local address. That's just not possible. It has to have a link local address, okay? Now, having said that, when they have link local addresses, they would only work up to this portion, right? Because the routers don't forward link local addresses, right? So these routers can talk to each other because they are on the same link using link local addresses, and the computer inside the branch can talk to each other because they are on the same local link, right? But these branches cannot talk to other branches with local link addresses because the router does not forward it. In that case, that's why you have the unique local addresses. You would have to assign everyone unique local addresses. So every device must, in that case, have unique local address, every device. So that would be a secondary thing you'd have to configure other than LLA. I hope that answers the question.
Yeah, this is the answer. Maybe I asked it too much, too early. Maybe this will be explained later. I'm sorry.
Yeah, no problem. I see another question, and this would be the last question I take in the middle. Then I'll have to continue. Okay. Question, please. Rodmelo, you are raising your hand. I don't know if you want to ask a question or not.
You answered. I need just to raise.
Okay,
now.
so you're okay. You can lower your hand. Okay, I'm muting everyone again, and we'll continue. Okay. Okay, so that is the difference between linked local addresses and global unique addresses. Okay. Now let's see how we can configure them on routers. It's actually very simple. Just like in IPv4 addresses, you go to the interface mode. So you select an interface, gigabit Ethernet 0x0, and you say, instead of IP address, you say IPv6 address. So all addresses related to IPv6 now would start with IPv6 keyword instead of IP. So if you see an IP keyword, that means you're talking about IPv4 because that was the default IP address or stack. Now you have to type IPv6 every time you're talking about IPv6, and the rest of the command is same. Then you do address, and then you provide the address in /64, which is the usual prefix length that you would see with the IPv6 addresses. And this is starting with 2001. So this is an indication when you see that this is global unique address, because global unique addresses starts with 2001 up to 2000 up to 3FFF. Okay, so any address between 2000 and 3FFF, you must know these are global unique addresses. So if you want to assign a global unique address to an IPv6 interface on a router, it is that simple. It's just like IPv4 address. Instead, just you say IPv6 and provide the address and /prefix notation. You can do that similarly on a Windows computer as well. So on a Windows computer, you would give a full IPv6 address if you're configuring IPv6, and obviously your default gateway should also be an IPv6 address. One different thing about IPv6 addresses when you are configuring it on the computer is that the default gateway, even though if you are getting a global unique address for a computer, the default gateway can be both. You can either use the global unique address of the router or the link local address of the router, which would be starting from FE80, right? That would be also correct, because your computer can still talk to your router, to your default gateway, because your computer and default gateway must be in the same local area network, right? So they are in the same local area network. So they can communicate using link local addresses as well. And every router and every computer must have a link local address. So even if your router has a global unique address, it must also have a link local address as well. And in the default gateway section, when you're configuring your host computer to point towards default gateway, you can use either of those addresses and it will work fine. Okay. All right, so this is how you manually do it. But remember, I said in IPv6, you rarely do manual stuff. You don't do it. It's just showing you that it's possible, but we rarely do it, okay? We don't want to do manual stuff. In very specific cases, we do. But so what happens if you obtain an IPv6 address automatically? So if you do it automatically, you either would have in your network, you would either have a DHCP version 6 server defined who gives IPv6 addresses and other settings, just like in IPv4, you have a DHCP server right now at your homes. Your access point, the Wi-Fi access point is acting like a DHCP server, and all your computers are configured to obtain IPv4 addresses automatically. So your computers, when they boot up, they send a message, they send a broadcast, find a DHCP server, and they get IP configuration from the DHCP server. DHCP version 6 also works similarly, somewhat, that your computers can get the IPv6 configuration and other configuration from the DHCP v6 server, or there's another method. So now in IPv4, we don't have any other method. You can either manually configure it on your computer or get it from DHCP. If you configure your computer to obtain it automatically, and there is no DHCP server in your network, then what do you get? On Windows system, you get a PIPA. Your computer just assigns a PIPA which starts from 169.254. And if you see this, you would know that, oh, it means if my computer has an IP that starts with 169.254 subnet or network, that means my computer is configured to obtain IP from DHCP server, but it could not find a DHCP server, so it assigned itself in a PIPA IP. That's what happens in IPv4 cases. But in IPv6, that's not the case. If your computer is set to obtain an IPv6 address and there is no DHCP version 6 server available in the network, it can use something called SLAAC, the stateless link method, which is used. The link local address of the router will automatically be specified as the default gateway address. And we're going to look into how this works in upcoming slides. Okay, but remember that unlike IPv4, in IPv6 network, there are other methods to get an IPv6 address automatically. And that's why I keep saying we don't do manual things in IPv6 because we have so many methods. Even if you don't have a DHCP server in IPv6 network, there's still another method to get an IPv6 address and configuration automatically, which is called SLAAC. And there are actually two methods in SLAAC. There's a stateless SLAAC as well. And we're going to look into that, okay? But just remember, like IPv6 works differently, okay? All right. What happens if you, so we saw that if you want to give a global unique address, it is just like in just IPv6 address and give the address. That's the global unique address. What if I want to assign a link local address? Because remember, we said each interface must have a link local address, whether you give it or not, okay? So even though you're only giving it a global unique address, we'll go next and we will see that this link would still have a link local address, even though you haven't defined it, but it will have it. But you can also assign it manually as well if you want to. And if you want to assign a manual link local address, you just have to type link local at the end of the address. And obviously it starts with FE80, so that's also an indication that this is a link local. But you have to give it a link local address so that the router interface really considers it that this is a link local address. And this is just a manual way if you want to do your own addresses. If you don't do it, that doesn't mean this interface wouldn't have a link local address. It would still have it. It would automatically generate one and assign it to itself. Okay? And we are going to see that. Anyway, so before moving further how messaging works and how the SLAAC works, let's do something on our computer and see what my Windows machine have. Okay, so I'm gonna look at that and I'll open up CMD and see what my computer has, right? And before I do that, let me see where am I connected. So I'm connected to this Wi-Fi, and I just want to make sure that I'm also connected to the same Wi-Fi on my phone as well, just to show you a few things around. Okay. All right, that's okay. So let's see. So let's see if on my computer I have an IPv6 address. Although I haven't configured it, but let's see. So we do IP config, and we see what's going on here. So where's my lost my command line? Where is it? Where is it? Okay. So where is my Wi-Fi? So here's my Wi-Fi adapter to which I'm connected and getting internet right now. And it's connected to this network, and I have an IPv4 address. We have talked about this. This is how I got it from my access point using DHCP. It gave me a subnet mask and also gave me a default gateway. But notice I also have a link local IPv6 address that starts from FE80, and there's a full address. Now, this is the link local address because my computer is at this point is dual stack configured, which we discussed in our initial slides. What is a dual stack? That my computer has a capability to run IPv4 and IPv6 simultaneously. And all you guys of computer, all the modern computers are capable of that. Even our mobile phones are capable of that, okay? So we all have an IPv6 capable devices, and they're all dual stack for most part. So since it is capable of IPv6, it automatically generated a link local address and assigned it to itself. Although there is no DHCP server in my network that is giving me IPs or anything. So I don't have a global unique address at this moment, but I do have a link local IPv6 address, okay? And to show you I can use this IPv6 address and use this link local address, I'm also connected to the same Wi-Fi. My phone is connected to the same Wi-Fi, and I also have, and my phone also assigned itself a link local address. And let's see if I can ping that, my phone, okay? So it is also starting from FE80, and it is 9056 DAFF FE84 and 9FCE. There should be double colon at some point. Yeah, so it's here. So it indicates if I have 1 hex state, 2, 3, 4, and 5, means I'm missing 3 hex state, and that means there are 3 zeros. Okay, somebody asked a question about this person 9. I'm gonna come back to it. Okay, I'm deliberately not talking about it to show you something. So this is my phone, and they're connected, and my laptop and my phone both are connected to the same Wi-Fi, and they both have assigned themselves automatically linked local addresses, and they should be able to ping each other because they are on the same local area network. Because my Wi-Fi is just switching for him, so my Wi-Fi is acting like a switch for these two devices to communicate together, right? It's not forwarding anything; it's just doing switching. So through switch, two devices should be able to communicate using link local addresses. So if I ping that, most probably this is not going to work. Not because link local addresses can communicate, there's something else at work here. What is that? That is where we come back to this thing, the person 9. So the person 9 is a special index. It's it identifies the interface. Okay, it identifies the interfaces. So if my computer has multiple interfaces, which my computer has, just like a router would have multiple interfaces or multiple links, right? So we talked about this. Let's see, how do I define it for you guys? How do I define it? I'm just thinking of a method to define it for you. Give me a second. How do I show you first on this Windows machine? Okay. So let me run this command. Okay. So netsh interface IPv6 show interfaces. This is going to show me that I have different interfaces on my computer. I have a loopback interface, I have a Wi-Fi interface, I have VMware virtual interfaces, I have a local area connection 1 and 10, I have Bluetooth. These are all different network interface cards. Remember, I hope there's no confusion in this, that a single host can have multiple network interface card. A Bluetooth is a different interface card. My Wi-Fi is a different interface card. My RJ45 port, if I only have one, then that's a single network interface card. If I have two RJ45 in my computer, then those are also network interfaces card. If I have a USB port, I can connect a converter that converts it into RJ45 and multiple RJ45 connections, and I can connect it to a network using that. Then those are also considered different. Those USB ports are also considered different network interface card. So every computer has different network interface card, multiple network interface card, and each network interface card would have their own adapter settings, own IP and MAC addresses and everything, right? just like a router. So router has many interfaces, and every interface is a different network interface card, and every interface would have different configuration. So similarly, this is kind of showing like a router. My computer has all these different interfaces, and each interface has an index number. Just like in a router, you have every interface has a different name, right? Gigabit 0x0, gigabit 0x1, or fast Ethernet 0x0, fast Ethernet 0x1. So each interface has a different name to identify it. Similarly, my computer also has these index number. They're not exactly like a router, named not in that fashion, fast Ethernet or gigabit Ethernet 1x1 or anything, but they're named by index numbers to identify which interface we're talking about. So my Wi-Fi is index number 9. And that's what appears here, that my Wi-Fi, when it's using IPv6 link local address, it is connected on this interface. Why is that important? In link local addresses, that is important because link local addresses can appear on all interfaces. All interfaces would have link local addresses, and they all belong to FE80. So all the link local addresses around the world are from the same subnet, right? They have the same prefix. They all start from FE80. So they're all part of same local area network from that perspective, right? So if I say ping a device like I did here, where is it? Which failed. So when I said ping this device, which is my phone, it failed because my computer doesn't know where is this phone connected to, which interface to send this packet onto, because FE80 subnet or FE80 prefix is available on this adapter as well. FE80 is available here as well. FE80 is here as well. So computer doesn't have a way to identify on which interface this packet to be sent, unlike when we were doing IPv4 private IP addresses, because every interface in IPv4 starts with a different network. Like you can see here, if I have a different adapter, then it's a completely different subnet, right? If I have a Wi-Fi, it has a completely different subnet. If I have a Bluetooth, look at that, it has a completely different subnet. It's 193, which is a network portion. So when I'm doing IPv4, I can ping all these different networks, and the computer can find out by just looking at the network portion that, hey, this packet needs to go on this adapter. If I want to ping something 192.168.0. something, my computer knows this is on the Wi-Fi adapter or a network interface. So I need to send a packet on this interface. But when it comes to IPv6, if I ping something starting with FE80, suddenly my computer is now confused. Should I send a packet out on this interface or the Wi-Fi interface or the VMnet 8 or a Bluetooth or any of these, because all of them have FE80 subnet. So there's a problem. We need to solve this. And we solve it by identifying the interface numbers. So in this case, my Wi-Fi has the index number 9. And that's why with each IPv6 address, after a person sign, it identifies the network with its index number. So when I have to ping my phone, which is connected to a Wi-Fi, I have to tell this that send this packet on index number 9 or interface number 9, or in other words, send it out of the Wi-Fi network interface card. Okay. And if I typed it correctly, then it should ping. Let me see if I am typed it correctly. 9056 DAFF FE48, not 84. It's 489FCE. So let me just do it without this. It should still fail. Okay, so the IP is now correct. It's still failing. But if I provide the correct index number, then it should pass. So now it's pinging. Why? Because now I told it to use the Wi-Fi interface. That's where my phone is connected to. So it's using the correct interface, and now it's able to ping it, okay? Okay, so if we do NS lookup for, this is linked local address communication. What happens if you have a global unique address, which I don't have right now at the moment, but what if we just try, let's say if Google has something. So if you do NS lookup on google.com, we see Google is using an IPv6 global unique address because it starts with 2. So anything starting from 2000 up to 3FFF are all global unique addresses. And the DNS resolved in IPv6, which is a global unique address for Google. But do you guys think I would be able to ping this? And I would also select that send this packet out of 9. In this case, it's not needed because now I'm not talking about linked local addresses. I'm talking about global unique addresses. And it would use a route table to find out where my internet connection is coming from to route this packet, right? Because now it's global unique address. Now routing is possible. So we don't have to pick interfaces in this case, but you can pick it if you want to. But it fails. We cannot ping it. Although I do have an IPv6 address on my computer, I still cannot ping Google on the IPv6, even if I do %9, let's say. It still fails. Why would it fail even though I have an IPv6 linked local address? Remember, the linked local addresses cannot be routed. So even though I have a linked local address, I can communicate with devices inside my network, just like I communicated with my mobile phone, which is connected to the same Wi-Fi. But I still cannot talk to the Google because I have a linked local address, and linked local addresses cannot appear on internet. It cannot be routed to internet. So that's why I cannot talk to Google yet with IPv6. In order to talk to the internet using IPv6, I would need either a global unique address, or over here also, I would also need a default gateway that has an IPv6 as well. So right now, my access point is not IPv6 enabled. It's not giving me any default gateway with IPv6. So I also need that, and I also need global unique address. So since I don't have those, I cannot communicate to the internet using IPv6. I hope this was clear now, difference between linked local addresses and global unique addresses, okay? Because I think I went too deep in it already. So similarly, when you're trying to ping devices in routers as well, when you're doing IPv6 and you want to ping something, in routers you would have to use ping 6. So in computer, my computer is smart enough. If I do this, where is the, so my computer is smart enough. If I want to ping the IPv4, it can ping it. If I want to ping IPv6, I can use the ping same command. But the routers usually, so my ping command is smart enough to find out, hey, if I give it a IPv6 address, and in a background, it will use the IPv6 code to ping this device. But when you go to routers, you have to actually say ping version 6 or ping 6 when you are pinging an IPv6 address. For IPv4, you just say ping. So ping is specific to IPv4, and ping 6 is specific to IPv6 addresses if you want to do it on a router, okay? All right, so now we move on to the topic of how does my computer or routers or devices, IPv6 enabled devices, dynamically get the global unique addresses, okay? So the devices can get global unique addresses dynamically through ICMP messages, ICMP version 6. So special protocol for, we have ICMP, and then we have ICMP version 6, which only works with version 6. So in ICMP version 6, we have some special messages that we don't have in IPv4. These are made specially for IPv6, and they're called router solicitation and router advertisement. We also have 2 more that are important, but we're going to talk about that later, okay? So what are these? Router solicitation messages are sent by host devices to discover IPv6 routers. So if you have a computer just like my computer and it boots up and it's connected to some network through their switches and other computers and all stuff, and then there's a router. When it boots up, it can send a router solicitation message to find out who is my gateway, who is my router here in this network. The question mark. It sends this is a router solicitation message. And then the router advertisement message are sent by routers to inform hosts on how to obtain an IPv6 global unique addresses and provide useful network information. So the router then, it can send it periodically as well, or it can send it as a response when it receives a router solicitation message. It can send that, hey, hi, I am your router or default gateway, and here is my IPv6 address. And other settings, if you need, like what are other settings? You need a prefix length, you need an IPv6 default gateway address, you need DNS settings, and other settings which a DHCP server can send, right? So these are the different settings that a router advertisement message can send. So this is a router sending a response, kind of. It's not usually a response. It can be also a periodic message that a router sends every 200 seconds. So it sends to everyone, to all hosts or specific hosts, if it's in response, that this is your network prefix and this is the prefix length, so that you know which network you are part of. And this is your default gateway address, which is his own address, which could be a link local address. And this is the DNS address and a domain name when you want to resolve the name. So you need a DNS server information as well, which usually you get in it from DHCP when you're talking about IPv4 networks, right? So you can see already that there is no DHCP in this network, right? There is no DHCP server. Still, this router can get all this information from the router using router advertisement messages. And the router advertisement can provide 3 methods for configuration in IPv6. It can give this information to the host and then can also tell it which method to use to create your own global unique addresses. Remember, the router is only telling it what is the network prefix and the prefix length. It is not giving it what is your exact IPv6 address. So remember, in global unique addresses, if it is /64, which is commonly it is, but it could be anything else as well. So that's why it's giving it the prefix length that, hey, your prefix length is /64, okay, but your network prefix, what is my network prefix? Well, your network prefix is 2000 /64, okay. That shows, so computer knows that this is my prefix 000 /64 up to here. So this is my network portion. Okay, got it. This is where it comes interface ID. What is that? Well, the router is not giving it exactly what is that. The computer or the host has to figure it out himself. The router only tells it which method to use to figure it out. Either you can use the SLAAC method, or you can use SLAAC with a stateless DHCP server, or you can use a stateful DHCP, no SLAAC, without SLAAC. You have 3 methods to create the interface ID for yourself. So now the host knows which method to use. It will use that method to create an interface ID for itself. The router advertisement already given it the prefix and prefix length, the default gateway address and DNS addresses. The interface ID, you must figure it out yourself, okay? So we look into that part now. How would a computer find out the interface ID part now? It got everything else, but it still has to create the interface ID for itself, okay? So if the router advertisement told it to use the SLAAC method, then it will use the SLAAC method. When will it use a SLAAC method, or when a router will tell the host to use a SLAAC method? When we don't have a DHCP server. So if you don't have a DHCP server, which usually we wouldn't have, then the router would tell all the hosts to use the SLAAC method. Okay, the device now knows to use the SLAAC method. So a device obtains other information which it already has the prefix length and the prefix. So it already has this information gotten. It has this information. It only needs to figure out this. And it also knows that it has to be a SLAAC method. Okay. So the prefix is provided, and the device uses EUI64 or a random generation method to create an interface ID. That's all. It depends on the different operating system what they use. So if the router tells it to use the SLAAC method, then based on operating system, it can either use the EUI64 method or just create a random number to give itself an interface ID. And that's how now it has a full global unique address. That's how it works. Okay. So this is the first method. We're going to get to the EUI64. What is that later? Okay. So at this point, you can think if the router tells it to create its own interface ID, it just creates a random number. That's all. But it can also use this method, which we are going to discuss later. Now let's just focus on the other methods first, and then we'll come back to that. A router can also tell it to use a SLAAC and stateless DHCP. So a router administrator can instruct a device to use both SLAAC and stateless DHCP. The message suggests the device using following: SLAAC to create its own IPv6 global unique address, which is same as this. Use this to create your own IPv6 interface ID. And then the router link local address, which is the route advertisement source IP address. When the router advertisement was telling the computer communicating with it, inside its source IP address, it uses its own link local address. So that's how computer knows that what is the address of the router that is telling me to do these things. So it will look at the source IP, which will have the link local address, and it will use it as a default gateway address. So now it has the default gateway address. It also created an IPv6 using random generation number or EUI64 method to create interface ID, and it will get other information such as DNS server or the domain name from DHCP. Okay, so that's the second method. So first is the router is telling it to use the SLAAC method, in which it cannot get any other information except creating its own interface ID. That's it. If the router tells it to use the SLAAC method and the stateless DHCP, again, since SLAAC is involved, that means create your own interface ID using random number or EUI64, plus stateless DHCP is involved. That means you can also talk to DHCP version 6 and get further information like DNS servers and domain names. So the computer sends a router solicitation message. It receives router advertisement from the router. Router tells it to use SLAAC and stateless DHCP. So using SLAAC, it generates its own interface ID, and then it gets the DHCP IP. It talks to DHCP to get further information like DNS server and domain name. That's SLAAC and stateless. In some cases, it would tell the host to, hey, just use DHCP. Talk to DHCP to get everything. In that case, the computer talks to using RS message, router solicitation message, talks to router. Router tells it using router advertisement message to use the DHCP. You talk to DHCP, and you get all the configuration. That's a stateful DHCP, which can give you everything. So it will give you the exact global unique address, the exact DNS server address, the exact domain name, and anything else that's configured on DNS. It will give you everything. So this is the last step, is exactly like the IPv4 DHCP. You get everything from DHCP, that's it. So there is no SLAAC involved in this case. When there's a SLAAC involved, that means you have to create your own interface ID, okay? So again, when SLAAC method is involved and you have to create your own IP address, which method to use? You can either use a random method or EUI64. So this, you would have to do it. So what is EUI64? EUI64 method is nothing but using the computer would use its own MAC address to create the interface ID. So the MAC address is 48-bit, but the interface ID is usually 64-bit. So to create a 64-bit address from the 48-bit MAC address, you would, in the middle of MAC address, just add this FFFE. You add 2 hex bits, and the 7th bit from the start. So the 7th bit from the start would come at this point. There's a 0, which is always 0, indicating a vendor given MAC address. Just flip it to 1 to indicate this was manually created. It's not a vendor given MAC address anymore. So if you flip that, the C becomes E. So in different cases, it would become a different thing. So this is how computer creates an interface ID if it is using EUI64. And you can actually see which device uses what method. So if I look at my device, it also, for the link local addresses, it also uses the same method. But if I want to see my MAC address, I can see if my link local address is using EUI64 or a random number to generate its link local address. So this is my Wi-Fi device. This is my link local address. And this is my MAC address. And you can see that my last 64-bit does not match with anything in my MAC address. So that means the Windows operating system just uses the random method. It doesn't use the EUI64. So it's not that important. But some devices like Linux maybe, or maybe Cisco routers, some specific model could be using EUI64. It's up to the operating system which one it uses, okay? This is randomly generated, which is what we saw in our operating system as well. So it doesn't have to be EU65, EUI64, okay? The same process is used for link local addresses, and that's why I was checking my computer. I only have a link local address. So all link local addresses start from FE80, but the last 64 portion could be generated either using EUI64 or could be randomly generated, which was randomly in our case, okay? This is what we have already seen. In my computer, it was not using MAC addresses to generate it. It was just random. You can also see it on the routers. If you do show interface gigabit Ethernet 0x0, so it will show you that here is your MAC address, the physical burned in address. It's also called burned in address. And if you see that your if you do show IPv6 interface brief, you'd see that its last portion is using the MAC address with FFFE inserted in the middle, and the starting point you see, instead of 70, it is 72 because the 7th bit is flipped. So if you convert it to binary and flip the 7th bit and then convert it back to decimal, the 0 becomes 2. All right. So we also have packet tracer activities to reinforce these learning and see how you can configure these IP addresses on servers and clients and routers and make them communicate together. And a video for that lab will be provided to you. We also have IPv6 multicast addresses, just like in IPv4 addresses. We have 2 types of multicast addresses. They always start from FF00, and we have well-known multicast and solicited node multicast. Okay, multicast addresses can only be destination addresses. We already know that. You cannot have a multicast addresses in a source address. It's always in a destination address. And well-known IPv6 multicast addresses are assigned and reserved for predefined groups of devices. And there are 2 common IPv6 assigned multicast groups. There's all nodes multicast group and there's all routers multicast group. So all nodes is FF021 and all router is FF02, :2. What is all nodes multicast group? This is a multicast group that all IPv6 enabled devices join. If there is a computer with an IPv6 address, IPv6 enabled, it is automatically joining this group. You don't have to configure it. If you check their multicast configuration, it would say it has already joined to FF02, all the IPv6 devices, whether it's a router, a computer, or a mobile phone, okay? It will be part of this. So a packet sent to this group is received and processed by all IPv6 interfaces on the link or network. So this multicast group is essentially acting like your broadcast. If in your network you have a need, like in IPv4, you wanted to send a packet to everyone in your local area network, you would have to send it to the broadcast address, which is 255.255.255.255, right? So in IPv6, we don't have broadcasts, but if you have a need to do that, instead of using a broadcast, you can send it to this multicast group, FF02 $1. This is all node multicast group. All the IPv6 devices have already joined it. So if you send it to this, that means you're sending it to everyone. So it's exactly like a broadcast. Then you have an all router multicast group, which is a multicast group that all IPv6 routers only join. So all routers must join this one as well and this one as well. But computers will only join this one, not this one. Okay? So if I have a router, it is part of two groups. The FF02 $2 and 1. If you have a computer with IPv6, it is part of only one group, the FF02 $1. Okay. So only routers. So if you want to send a message only to all routers, then you would send it to FF02 $2. So you would know that only all routers are part of this group and only they will receive it. So router becomes a member of this group when it has enabled IPv6 router with IPv6 Unicast routing global configuration command. So as soon as you enable IPv6 routing on a router, it joins this IPv6 group. So if you have a need to send a message just to the routers, not to all hosts, you can send it to this group. And router uses this in their routing protocols to communicate with each other. Okay. So these are well-known IPv6 that all host joins, the first one, and the second one, all router joins. And then we have solicited node IPv6 addresses, which are multicast addresses similar to all nodes multicast addresses. Okay. And a solicited node multicast address is mapped to a special Ethernet multicast address. So this is a special multicast address which is mapped to a special Ethernet multicast addresses, meaning this multicast address, which is a special, when you use this as a destination, it has a mapped multicast MAC address which you would use in Ethernet destination as well. So if you want to send a broadcast or a specific message to a specific group, to a specific IPv6, you would use a special multicast MAC address as well that is only reserved for this special multicast group for IPv6. So in that case, the Ethernet NIC can filter the frame by examining the destination MAC address. So when a computer receives this special MAC address, which is part of multicast access group, it knows if it has joined an IPv6 group just by looking at MAC address, and then accepts if it has joined it. Okay. So there are again labs that you would get in videos for. And then we have subnetting in IPv6, which is quite easy. You don't have to fear subnetting in IPv6, just like you have to do a lot of calculations in IPv4. In IPv6, you don't have to. When you get an when you get a global unique address, you usually get a prefix. So you get a prefix of /48, and then you have a 16 bits of subnet ID, and then you have 64-bit of interface ID. So this is the whole /64 in which the /48 is prefix that you cannot change, that is fixed from your ISP. And then plus you have 16 bits, which are just a hexstat that is assigned to a subnet ID. And you are allowed to keep changing that to create new subnets. So for example, you get this 2001 DB8 ACAD /48. So the /48 means this part /48 cannot be changed, but the next /16 bits can be changed. So your address is 2001 DB8 ACAD 00/64. So this is one subnet. This is second subnet. So different branches or different local area networks can get these all different subnets while their global prefix is same, but their subnet IP is different. So that's how you create different subnets in IPv6. You don't have to do any calculation. It's usually just following this, okay? Yes, we're gonna take a break, just finishing this up. We're almost at the end. So just an example again, same example. So if you have a network, so if this is a separate network, right, you get this entire network gets an IP address from this 2001 DB8 ACAD 0001:/64, and this is a different network. So you get this one becomes 2, the 002 subnet ID. This one becomes, this is a different network, this becomes 3. This is a different network, this becomes 4. So you don't have to do any subnet calculation in IPv6 like you would have to do in IPv4 if it was the case. You just change the subnet ID and that's just a different subnet for you, okay? And on a different interfaces on a router, because every interface on a router must be a part of different subnet. So you can see it that you would assign, so 0x0 interface would get the subnet ID 1, 0x01 gets subnet ID 2, 01x0 get the subnet ID 3, and so on. So this is how you're differentiating different subnets in global unique addressing in IPv6, okay? To finish this module, and we're going to take a 10 minutes break and start a next module which is related to this, and we'll see if we can finish it. It's easy. We've already talked about the router solicitation message and router advertisement message, which is part of ICMP. So we're going to discuss ICMP both in IPv4 and IPv6 and see how they're different. It's a small portion. We're going to come back and finish that off as well, okay? So we'll get a 10 minutes break and come back. So see you after the break, okay? Okay, now that we have looked at the IPv4 and IPv6, both how they work and how we represent and how we subnet and everything, let's talk about the ICMP. And while we talk about the ICMP, remember on the OSI layers, we are still at the network layer 3. So IPv4, IPv6, ICMP, we're still talking about these services at the IP layer or the layer 3 network layer, okay? So ICMP is another protocol that works at the network layer, which is, we are going to explain like what is the purpose of it. It sends ICMP messages, which is what makes the ping work, which makes the trace route work. So we're going to look at how the ping actually works. We keep using ping for connectivity testing, and it is a tool. Ping is a tool, a command line tool that uses ICMP messages, which are used in OSI stack at layer 3. So let's talk about the ICMP messages. So what is an ICMP? So also that ICMP for each version of IP is a different protocol. So for version 4, we have ICMP version 4, and for IPv6, we have ICMP version 6. So what is an ICMP? Internet Control Message Protocol, which was created to troubleshoot the network layer problems. It provides feedback about issues related to the processing of IP packets under certain conditions. So it is a tool, and a ping is a tool, traceroute is a tool, but ICMPv4 or ICMPv6 is a protocol at a network layer that helps us troubleshoot network layer issues. It gives us feedback about issues, and we can use it to troubleshoot connectivities at layer 3. ICMP version 4 is the message one protocol for IPv4. ICMP version 6 is for the IPv6. And it obviously, when we talk about ICMP version 6, anything version 6 has additional capabilities that we did not have in the previous version. Okay. There are messages that are common to both version 4 and version 6, like host reachability, destination or service reachable, time exceeded. So these are the messages that helps us like what is happening at the network layer. It gives us messages about host reachability. So I have an IP address of 192 something, and I'm trying to ping it. These using ICMP protocol, it tells me whether I can reach to this IP or not. That is the host reachability message. The destination or service unreachable. So if I have a host that talks to a router, and then the router has another router and a whole connection, and then there's another device, And if I send a message ICMP, this router will forward it to this, and sometimes these routers don't have a route to this service, right? This device, it cannot forward it for whatever reason. It doesn't have a route. That the router can send you a message, a destination or a service unreachable, telling you that, hey, you want me to forward this packet to a specific destination, but it's not reachable. I don't have a route for it, or it is blocked, or the firewall is not allowing it. So it can send back a feedback message to you, although your packet has not reached your destination, but the intermediary device like a router or a firewall can send back a response to you telling you that I cannot forward your packet for some specific reason, whether it's firewall blocking it, ACL blocking it, or I just don't have a destination unreachable, like I don't have a route for it, I don't know how to reach it. Or it can send you back an information, either a router or the destination device, or any router can send you a feedback that time exceeded. Remember TTL at IPv4, there's a TTL header field, which has a timer, which has a hop count. So every time a router forwards a packet, it reduces 1 from it. And it keeps reducing this number. Then when it reaches 0, the router will discard that packet. And when it discards, it sends back a message to the original source with a time exceeded message. That's using ICMP. So it tells you that, hey, your packet was dropped at this router because it exceeded the time, the TTL value. It cannot further forward it. So whatever destination you're trying to reach, it's so far away, or there's a routing issue that your TTL expired. So your message was not able to receive it. So you see these messages and feedbacks from intermediary devices or end devices telling you something helps you troubleshoot the issue, like why I am able to connect to something or why I'm not able to connect to something, okay? That's where ICMP protocol is helping us at the network layer. So this is an example. So when you do a ping, ICMP, so there are different types of messages, okay? So when you do a ping, it's called echo message, which can be used to test the reachability. So when we are doing ping, we are just testing reachability using the echo message. There are different type of messages. Echo type of message is the one that we send when we send a ping, when we use a ping and provide an IP. So your computer creates an echo message and it sends an echo request. It's called an echo request. You send an echo request to this computer and this computer sends you back in called echo reply. So a destination host responds with an echo reply. That's what's happening with the ping. And using this echo request and echo replies, which by default, when we do ping, my computer sends 4 echo requests and we get usually 4 echo replies. And with each reply, we get further information. We get the statistics about the connection between 2 devices. We get the TTL information, we get the latency, we get the round trip time of our communication. So it gives us all these statistics and we collect it and we understand that these 2 computers can communicate together with these specifications between them. With this is the latency or round trip time and this is the TTL between them to benchmark the connectivity and see how good our connection between these 2 devices are at the network layer, okay? So we have a bunch of destinations. So that's when the echo request and the echo reply, you get an echo reply, which you have when you have a connectivity, right? But most of the times you would not have a connectivity. And in that case, you have different messages telling you why you don't have a connectivity with the specific destination you are trying to reach. So when something is unreachable, there are different codes that you would receive, like net unreachable, host unreachable. Well, net unreachable means the whole network. We cannot reach the whole network that you're trying to reach. Maybe there's no route with the router. Host unreachable, maybe we can reach the network, but we couldn't reach the host. So you get the one type of unreachable code. So you know, okay, this is not a routing problem. This is probably a host problem. We can reach it, reach the network, but we cannot reach the very specific host inside the network. Maybe the host is down, maybe it's shut down, maybe it has a connection issue or something. There's a protocol unreachable or port unreachable, meaning you have reached inside the host, but the host doesn't have a protocol. Its protocol is not reachable, or you reached to the host, the protocol was reachable, but whatever port, the application you want to talk to, that application was not reachable inside that host. So there are multiple ways why your packet did not reach. Either your packet, the destination you provided, you couldn't reach the whole network, or you could reach the network, but there was no host inside the network. You get the error code 1, the unreachable code 1. Or you could have reached the host, you reached the host, but inside the host, there was no protocol. Maybe you're using TCP or UDP and that protocol wasn't even there on the host. Just an example. Then the host replies with unreachable code 2 that, hey, okay, your packet reached, but there is no protocol. The protocol you specified, that's not here. So you know it's a protocol issue now. So focus on that. And sometimes it's like you are using everything correct and packet is reached, the protocol is there, everything, but the port number that you used in a destination on that host, that port number is not available. There is no application listening on that port. So it would send back that a port is unreachable, and that's something which traceroute uses a lot. Okay. So similarly, this is ICMPv4. These are messages. In ICMPv6, you also have these kind of messages and some more as well, different. So 0 would be no route to destination, network unreachable, almost same thing, just a different name. No route to destination means your network cannot be reached, right? The unreachable code 1, communication with the destination is administratively prohibited. For example, a firewall is blocking you to reach this specific destination. So your host is unreachable in that case. Number 2 is beyond scope of the source address, means your source is being blocked, or you're not allowed, or you're using a source IP that is not allowed to go beyond this to this destination. So there's problem with your source address. Maybe you're using linked local address and trying to ping a global unique address. That's not possible, right? Or unique local addresses. So number 3, address unreachable. For some reason, this address is not reachable. Port unreachable, again, like the application is not available. No port is listening on this computer on the one that you're trying to communicate. These are different codes in IPv4 and IPv6 that helps you troubleshoot your connectivity issues between two devices, two protocols, or two ports at the end destination, which is basically meaning application level. TTL, we talked about the TTL. So if your TTL expires, if you're going through so many hosts that your TTL, that each router at each hop keeps reducing or decrementing it by 1, and it keeps doing so. If your TTL was 128 and your destination is so far away that it has to traverse 128 routers, eventually your TTL value would reach 0 because every router in the path is reducing 1 from it. Eventually, the last router, when it reaches 0, it will discard it and send you a packet which says your TTL expired. And this is the router that is telling you that, hey, your TTL expired. I'm replying you because I discarded your packet. It did not reach its destination. The reason is that when the packet reached to me, its value became 0. When I reduced 1 from it, its value became 0. So I had to discard it. I cannot forward it. So instead, I'm sending you back information that your packet TTL expired in transit so that you fix whatever you need to fix. Okay. This is also something the traceroute uses a lot, and we'll see how traceroute uses it. Okay. ICMP version 6 has some special kind of packets features that the ICMPv4 does not have, and 2 of them we have already seen. So router solicitation and router advertisement. We already saw that the IPv6 routers and IPv6 hosts uses this. So the IPv6 host use router solicitation message to find its configuration, IP addresses, default gateway, right? It sends that to find the router. Who is my router? Give me this information. In the router advertisement messages are the router sending it to the host to give them information like what is your network, what is your prefix length, what is your prefix, whether you use SLAAC with DHCP, stateless DHCP, or stateful DHCP without SLAAC to get yourself interface ID or configuration, right? So these are also using ICMP. There are 2 more that ICMP has, ICMP version 6, they're called neighbor solicitation and neighbor advertisement. So router solicitation or router advertisement is between host and router communication. Okay. Neighbor solicitation and neighbor advertisement is host to host communication. So host, when wants to talk to another host, they can use ICMP neighbor solicitation or neighbor advertisement. This is messaging between IPv6 devices, including duplicate address detection and address resolution. So in IPv4, if we have an IP and we want to find a MAC address, what does a computer do? It uses address resolution protocol to find it, right? So address resolution protocol sends a broadcast saying, who has this IP, please respond with your MAC address. Everyone else sees that broadcast, they don't respond. Only the one with that IP would respond back and show its MAC address. So that's how computers find out what is the MAC address of this specific IP and put it in the ARP table, right? In IPv6, we don't have ARP. Instead, we use neighbor solicitation and neighbor advertisement. So using neighbor solicitation, a computer might ask, who has this IPv6? Give me your MAC. And with neighbor advertisement, the computer that has the IP, it would send back its MAC using neighbor advertisement. Similarly, these messages can also be used to find duplicate IPs. Somebody in previous module asked, how does IPv4 find if there is a duplicate IP? What happens? So that's happened. So if a computer thinks, when a computer gets an IP, it can send an ARP for its own IP. So if I get 192.168.0.10 IP, if a computer wants to see to make sure that no one else has this IP, the same computer can send an ARP broadcast in its network saying, who has 192.168.0.10? Please respond with your MAC address. If nobody responds in a specific time, then the computer knows that no one else has this IP, so there are no duplicate IPs. If somebody responded back, well, the computer knows there's a duplicate IP and there's a concept, it would show on your computer notification there's a duplicate IP, fix it. Similarly, in IPv6, we don't have an ARP, but we have neighbor solicitation and neighbor advertisement. So in neighbor solicitation, a computer can send that, hey, who has this IPv6 address? And if somebody responded with MAC address, then he would know there's a duplicate. Okay. So we already talked about this. We have discussed this, how router solicitation and router advertisement works, but we talked about it that a computer must send a router solicitation message to find settings, right? And then the router would respond back with router advertisement. But in reality, router advertisement messages are sent by routers every 200 seconds. So it's not waiting for someone to send a router solicitation message. It sends router advertisement every 200 seconds. So even if nobody is sending a request, everyone still gets router advertisement messages and they can listen to it. Okay. And it can include the prefix length, DNS addresses, domain name, and the SLAAC, and information about whether to use a SLAAC, which default gateway, or what is your DHCP, and those kind of configuration as well, which we discussed in very details in previous module. Okay, so we already talked about that router advertisement messages are also sent in response to router solicitation messages. So this is a use case we already discussed a lot, that computer booted up will just ask if there's an IPv6 router on network. I need to know to get my IPv6 information, and R1 will reply with RM message, giving it its prefix length, and also telling it to use a SLAAC to create its own global unique address, or get the stateless DHCP or stateful DHCP to get all further configuration, right? We also have the neighbor solicitation messages, which can be used for the duplicate address detection, which I already discussed. So it can send a neighbor solicitation message for its own IPv6, and if it got a response, that means there's a duplicate, otherwise there's not. And it can use this to communicate. It can also use this to find MAC addresses of IPv6 as well, which is defined here. So instead of using address resolution protocol, using network solicitation messages and network advertisement messages. The computer can ask who has this IP, and the computer who has an IP can respond with its MAC address, and that's how we don't need address resolution protocol in IPv6. We can use neighbor solicitation and neighbor advertisement messages. Okay. How does the ping and traceroute work? So this is interesting. So ping we have used so many times, so I don't think I have to explain that any further. But here's something that you have to notice. In routers, when you do a ping, a successful ping is denoted by an exclamation mark like these. An unsuccessful one is denoted by a dot. So usually you see this pattern that first time when you ping something, you miss a packet and then it starts communicating, and after that all the packets communicate. This is a pattern when you see, you must know that this is also a trick question. It is asked in interviews a lot, that why are we missing this one packet? The reason for that is that we have discussed it previously as well, is the address resolution protocol. Because the first time when you ping this, inside this computer ARP table, we don't have MAC address for this IP. So in the background, this ping goes into wait mode, and it basically almost has a timeout of 2 seconds or 4 seconds defined by, depends on different operating system. So it goes into wait mode or goes on to hold, because it cannot ping it yet. It cannot initiate or create the frame yet because it doesn't have a MAC address. So in the background, another process starts for the address resolution protocol to find the MAC address first. So ARP goes out, does the broadcast, gets the MAC address, puts in ARP table, and sometime or most of the time, your ping, which is on the hold, times out because more than 2 seconds has been spent. So this one message is because of that timeout until the ARP gets the MAC address. And for the second time, when it's initiate a second packet, the ping, until then ARP has done its job and there's a MAC address in the ARP table, and that's why it starts pinging from the second packet and onwards. So that's the reason for this pattern, that usually one packet is dropped initially, sometimes even 2 packets if ARP takes longer, but then it starts communicating. Okay. We've already pinged the loopback a lot, 127, but maybe we did not ping the IPv6 one, so I will do that. So IPv6 is just : 1, so you can see we can ping that as well, and obviously 127.0.0.1. or any IP in 127.0.1, because the whole block 127.0.0.0/8 is loopback address in IPv4. Okay. Similarly, we have one in the pinging the default gateway. So definitely, if you have a default gateway configured, it's a good test to ping your default gateway to see if you can communicate with the default gateway. So it's a good test to confirm that you can reach your default gateway. And that's one of the troubleshooting steps when you don't have internet access. The first thing you see, like, hey, can I reach my default gateway even? Because if I can't reach my default gateway, I cannot reach to anything else. So that's the first test we usually do. Pinging, when we ping the remote host, we know how we ping a remote host. So if you are on this 10.0.0.1 network and you want to ping something here, this is 10.0.0 network, and this is 10.0.1 network with /24. So they're 2 different networks. If you want to ping from here to here, obviously you have to go through router, and that means we have concluded that with a lot of details how computer finds out when it starts to ping either local computer or a remote computer, what is the difference between them, how it finds out whether it needs to send it directly using the destination MAC address if it's the local computer. If it's remote computer, then instead of finding the MAC address for the remote computer, it finds the MAC address for its default gateway and then sends the frame to default gateway, and then the router will look where the destination network is. So it's here, it knows which interface it needs to forward it, and then it will forward out that interface, and that's how it reaches. So your ping, echo request, and echo replies work that way for the remote computers. Trace routes. So trace route is another troubleshooting tool like a ping that can show you the whole path your packets are taking to reach to a specific destination. So let's use it to, let's say, because we're using Google a lot, so let's do trace route, if that is the command. Sometimes it's trace RT in Linux, I think. So if I do trace route.8.8, it is not, so it might be trace RT, yes. So trace route might be the Linux command, trace RT is the Windows command. So if I do trace RT or trace route 8.8.8, what I'm essentially getting a response is that it is showing me the whole path my packet is taking to reach that destination, that the Google servers, okay? And by showing the whole path, what do we mean? By showing the whole path, we mean is that it shows me all the hops in between my destination. The hops are the routers, the devices that are doing the routing function, okay? So the first thing, it's also giving me statistics on how far or what are the link statistics between that intermediate device and my device, right? So the first device it's showing me, it is always my Wi-Fi access point. So the first hop is my access point, and the second device is somewhere in my ISP that is giving me the connection to my access point, which is the WAN connection through which I'm getting internet. And then it is still the ISP, because I can see it is still using some private IPs, but they can do network address translation at the carrier grade, so I can still see them. And then from here, I can see the public IPs with, this is the host name, this is the domain name of the router. It's showing me the domain name and also the IP address. From this, I can see this is specifically my ISP domain, that is. So it's still routing within the ISP from one city to another city. And this is where it reaches up to the submarine cable. So it's reaching to a city in my country, which is closer to the submarine cables, to the sea. And that's where it's connected to another country and another country. And after 3 devices through the submarine cables, it has reached to the Google servers. And this is the final device where my packets are reaching and ending. Now, traceroute does that, and it's very good for troubleshooting and finding the link connectivity. And if there's some issue between intermediate device, we can see which device stopped forwarding our packets, and we can understand, is it our own device inside our network that is stopping our communication, or is it someone else or ISP's device that is stopping? It helps with those kind of troubleshooting. But how does it do that? How does it find out what are the intermediate devices? Okay, so remember we said TTL, that's what it uses. So when you have a computer and that's connected to your access point, and then that's connected to a router with ISP and another router, and then eventually there's a server that you want to ping, right? So it was 8.8.8 that I wanted to ping. So when my computer starts a traceroute is a tool. So it uses TTL to trick all the computers. So it creates a packet with a destination of this and source of mine and everything as usual, a frame, how the frame, everything. But it uses a trick with the TTL. Inside the TTL field, that is the IP header, right? It sets the value of 1. So TTL value is set as 1. And it sends the packet to its destination. It will reach the first router. What does the router do? When it looks at the packet, it has to do forwarding, right? But remember, every time it has to forward a packet, whenever it receives a packet, it has to decrement the TTL value by 1. So it decrements the TTL value by 1, which is what right now? It is 1. So 1 minus 1 equals 0. If the TTL reaches 0, the router does not forward a packet. Instead, what? It drops it. And what did we say previously in the ICMP unreachable has different codes of messages, right? So when it drops, it sends an ICMP unreachable message with the code of 4, I guess it was, which means TTL, time exceeded. So it sends a feedback with ICMP unreachable, type of code is 4. And this computer receives it. And when it receives it, it shows its source IP as well, right? That I am 192, and that's how it says, whatever IP it is. So that's how, so my access point is sending me back unreachable packet with type of code of 4 and showing its own source IP. And that's how when I receive this packet, I know, okay, this is the source IP, and it sent me back in unreachable type 4 code, ICMP code, and that's how I know this is my first hop. So I create a table, so this tool, traceroute, creates a table and shows me this is my first hop. Then it creates a second packet, and it creates a second packet with TTL value 2, sends it here, it decrements 1, so 2 minus 1 equals 1, right? Now it will forward it. When it forwards it to the second hop, it's 1 minus 1 equals 0 again. It will drop it. When this drops it, whatever IP this has, for example, in this case, it has 1017, so 1017 whatever, it will send me back time exceeded ICMP type 4 unreachable message. And it shows its source IP. So now I know this is my second hop. And I'll create a new packet with TTL equal 3. Send it to this, 3 minus 1, 2. Send it to this, 2 minus 1 equals 1. Good. Send it to this, TTL 1 minus 1 equals 0. Drop it again. So this will drop it and send back a message. So now I know who is the third route. And we keep incrementing the TTL until eventually we reach this one. And then we get a response from this one. And because this is now a server, what kind of message it would send us back? It will not send us that the unreachable type of code is 4 time exceeded, because now this is not a router, it is a server. It cannot send us that TTL unreachable. When a message reaches it, it doesn't have to forward it. It doesn't have to look at the TTL at all. That's the router's function. It doesn't care about TTL. The message reached it, that's fine. Now it has to own it. The destination was itself. So it doesn't have to do anything with the TTL. So how my traceroute command knows that this is the final destination and I don't have to increment a TTL by one more again to see? Well, when it's sending these messages, the destination port, which is something we will be learning next when we start to the next OSI layer in the next class, which is TCP or UDP, the destination port is just use some arbitrary port that is not available on this server. And we saw these messages. If let me go back to those messages. So what was the time TTL? What was, I was just keep saying TTL decremented. So yeah, so ICMP4 time exceeded message. This is what all routers are sending you, and that's how you are finding the hops. But when the final message reaches the server sends you this message, ICMP type 3 message, port unreachable, because the destination port that we put, the traceroute puts in it, does not exist on that server. So the server sends back a message that, hey, whatever message that you sent me, I don't have that port. I'm not even listening on that port. So it sends an ICMP destination unreachable code with ICMP4 code type 3, port unreachable. So my computer or the traceroute command is receiving all these messages with TTL time exceeded, and that's how I know these are all routers. And eventually, from one of the IP, I receive a message that doesn't say TTL exceeded. Instead, it says port unreachable. And when it says port unreachable, that's when I know this is the final destination. So I stop my commands, I stop incrementing TTL, and I finish the command here. So I know that this is the whole path. Sorry, this was the last one. I need to hit enter. Okay, So that's how traceroute works to test the path. Okay, so then we have packet tracer activities for which you will get the video links of video recordings as well, so that you can complete your packet tracers, and please do your quizzes in your account as well. I will open it up now for question and answer session. So if you have questions, please ask now. I'm unmuting everyone. Now you can mute yourselves, start asking questions, okay?
Sorry, Mohammed, I have just one question.
Okay, yeah.
The packet tracer video quizzes, where are we supposed to find it precisely?
Where are you supposed to find what?
The packet tracer video quiz that you are mentioning.
The videos links.
For the packet tracer quiz or for the packet tracer practice.
That's in your group. Did you join the class recording group here? In here, I have a list of all the videos, and then you have lab videos. So if you open up the lab videos, you'll go to a Google Drive folder that is shared with you guys.
So there's another group called class recording.
Sorry, say that again.
There's another group called class recording, right?
Yes, that has recordings for all the labs. If you're talking about where are the lab files, the lab files are inside your Netacad account. So each module, if you go to module 13, if you're studying from there, you would see that there are packet tracer files that you can just click and download from there.
Yes, I've downloaded some packet tracer files for practice from the Netacad. I've done that. I'm just talking about the videos that you are always talking about.
Yeah, so I showed you where the videos are.
Yeah.
Okay. All right. Thank you. Anyone else with a question?
Mohammed?
Yes.
I've noticed when you're doing the ping,
Yes.
it's different when you're doing from your PC and from the switch. Why does it not fail? The first ping does not fail mostly when you're pinging from the PC, but it fails when you're pinging from the switch.
That's because, well, it does, but you haven't seen it on my PC probably because I don't have anything in my network that I'm pinging usually, right? So anything that I'm pinging is already because the PCs, well, let me put it that way. The PC has a lot of applications that are working in the background, right? There are a lot of applications. If you open up a task manager, how many you see? You almost see like 50, 60 processes running in the background, right?
Right.
So my PC is always communicating with other devices in my network through some software application that are running in the background. So they're already communicating. So because if they're already communicating in the background, they already have done the op request and find out the MAC addresses. So it's mostly always inside the op table. It's filled. When you do it on a switch, on a router, the switch and router does not have a lot of processes running in the background, unnecessary processes. So that's why usually if you're pinging some device, it is almost always the first time you're pinging it. There were no communication with that device before you're pinged. So in computers, it's usually some other application already established communication, some broadcasts are already running, some share services already running, some network services running, and that's why it's already there. That's why you don't see it in PC usually. That's all. There's no other reason.
Okay, thank you.
Mohammed?
Yes.
Yes, can you send me the link to the class recordings? I can't find it on this WebEx application of mine.
I will send it again. It's in your main group as well, but I'll send it again so it's fresh. If you also check the pinned message on the group,
if I check
on the top there's a banner. Oh no, that's just showing the meeting link. So I'll send it again. I'll send it again. Here it is. Let me
Can you
send
send
it
it
right
to this
now.
chat so that I can just join it immediately because I couldn't find any of
Okay,
sort.
let me send you a space link in this chat for the meeting chat, right?
Yes.
So that you can just join it right now. So this is the class recording link that I just sent in the meeting chat.
Unable to join this place. Try sending a message to the person who shared the link and ask if they or a moderator can add you to the space.
Are you on your mobile phone or are you on a website?
No,
did you download the desktop
I
application?
downloaded the WebEx application.
Desktop application. So
Yes,
everyone is joining it that way. Let me share it in the other group. So that's how everyone has joined this group from this link.
Yeah, it's the same message I'm getting that I am unable to join.
I'm not sure how everyone else has joined it, but I'm just going to stop recording right now. So because our questions are done, so let me stop the recording first.